this is not real time. This map right here is not real time. It's the simulator. On the telescope, this is a real time map. And so if you'll go ahead and click on Enter RANDEC, that's the coordinates in the sky. That's like the address of the object. And for the simulator, they want you to go to a specific target. If you'll come down here to right ascension, click on that. There you go. And enter 09, colon. There you go. 55, colon. 33. And then change the declination to, you ready? There you go. 69, colon, 04, colon, 00. And then the name of this is M81. Okay? Go ahead and click on Continue. So what we've done is we've entered the address, the name and address. This is addressing your envelope or addressing your telescope in this case. And then it'll show you what part of the sky you'll be looking at. This red block shows what part of the sky you'll see, and then if they know of any objects that are in that block, they'll show up. Like you can see Bode's Nebula there, which is M81, and then SN 1993J, supernova 1993J. And then I'm not sure if all these stars are accurate, but the important thing is you're usually looking, when you're doing this, you're usually going for a pretty picture, something like a galaxy. So at this point, we've confirmed that our target is in our field of view, right? Everyone agree it's in the field of view? What about our telescope operator? Yeah, okay. So if you will tell the telescope to move now, and it doesn't actually slew this fast, but we didn't want to have, real-time slewing. Okay, and then go ahead and click OK, because it's now pointing at our target. What do you think? You want a color image or black and white? Color. 99 out of 100.
Yeah.
Okay. If you'll enter how many seconds, and it says over here that for the simulator you want to do 30 seconds. Okay. Very easy. And then go ahead and make the observation. And that's really what it would look like. They don't take as long on things like slewing. The integrations, it would be taking 3 pictures with 30 seconds for each picture, plus a minute to read the picture off the camera. So it would actually be, nearly 5 minutes of time to take that image, but they've compressed that. And then go ahead and click OK. There you go.
There it is.
And that's the kind of thing that you actually see. Now, is that easy?
Yeah.
You could do that again, couldn't you?
Yeah, with the right instructions.
Yeah. Well, do you think you could walk through it one more time without me telling you? No, okay. But it would be pretty easy to get to that point, wouldn't it? Okay. All right. Let's give my lovely assistant a hand. Thank you. All right. So now we know what the Pfalz telescopes are like. This is the real-time control interface. The telescopes can also be operated in Q mode, which means basically that I program the telescopes to do the observations. The advantage of doing that is when we operate in Q mode, we get the images faster. We have a few more options to maximize, to optimize the data. And the real biggie is you don't have to be awake at 3:30 in the morning clicking on the same button time and time again. You just let the telescope go ahead and do that. They're fully robotic telescopes. They can operate without human intervention. Pfalz North, I know, has gone for a couple weeks without anyone even keying in the door. So pretty nice, slick little instruments.
What
Yeah.
size are they?
It's 2 meters in diameter. Appreciate that. So the diameter, the primary mirror is 2 meters in diameter, about 80 inches around, for those of us who are still stuck on archaic units. All right? All right. Now, they're owned by a company called Los Cumbres Observatory Global Telescope Network, LCOGT. You'll notice that that I claim that I work for them. Technically, I don't, but they do provide salary support to make sure that I have time to work with a lot of students and make sure that the telescope is, the data gets to the researchers we want it to get to, right? Okay? And they're building a network of telescopes. The idea behind the Falks telescope was it was built for school children in England. And the nice thing about that is the kids can go into school during the day, have a telescope and an outstanding sight that is available to them. So they go into their classrooms and they take all these images from the night sky here in Hawaii. Okay? Los Cumbres is building a network of telescopes worldwide. This map has changed in the last 20 minutes, I guarantee it. Every time the president of Los Cumbres has commented that every time he sees this slide, it's different. And I agree, I don't know quite what the status is. But the idea behind it is to have 5 or 6 different sites in North America, or in the northern hemisphere, and southern hemisphere, 3 in each, to build between 12 and 15 1-meter diameter telescopes, so about that big around, and 24 0.4-meter telescopes, so something like that. Fairly impressive network, and got to stop hitting the wrong button. It should be a fairly impressive network, and the telescopes will be as easy to use as we just saw Falks was, and a lot of time will be available to students and educational groups.
How many of these exist now?
None of them exist. There is one in Texas at McDonald Observatory that is operational. It's a 1-meter. The Falks North and Falks South both exist. So those are the 3 that exist. The 2-meter Falks South and Falks North.
Are the 0.4 meters, 16 inches, are those coming later?
The 0.4 meters are coming later. I've seen them. They've got them. They've got a stack of them built. They have the next 3 1-meters built, and I saw those. They were testing them, and when I was there a week ago today, I was in Santa Barbara. They had they had 3 of the 1-meters, and when they left for the weekend, the 1-meters were dancing around, except for one of them had gotten lazy and stopped. And so when I ran into the technicians at the bar, I told them that one of them had stopped, and they said, dang it, which one was it? Yeah. So they have deployed a 1-meter in McDonald. They have gotten first light from that, and some really neat images. They have poured concrete in Chile and South Africa, is my understanding, and so they're coming along. This ring will be built. There's still some question about how much of the northern ring will be built. They want to at least...
That one in the Canaries there in South Africa?
Yeah, in Tenerife. They're negotiating on that. They're also talking about China as a possible site. At the AAS, it was China, and now it's back to Tenerife, and I don't know.
I got it. Thanks.
So, all right. So the next cast of characters, and this is not a complete show bill. So, okay, these are our student astronomers. Every one of the pictures that I'm putting up here, they've done some work with data from the Falks telescopes. This is not all of them. In fact, I know there are 4 students here 5 students here that have worked with data from the Phelps telescopes, and they're not on here. So sorry guys, but those are the pictures I had. Do you want to get, okay, go get a camera. He's making a pouty face. All right. So when I'm talking about these projects, choose one of these faces and attach that face to the project, or choose one of the students in the room. You guys mind raising your hands if you've done work with the Phelps telescopes? Yeah. Okay. So choose one of those faces and attach it to these projects. May or may not be the right face to the right project, but you understand that these students are doing this kind of research. Okay, so here's the approach. Show them a pretty picture. I mean, this is pretty cool. This was taken by the using the Phelps Telescope North by some students here in Hawaii. And now, is that not cool?
It's very cool.
Yeah. It kind of gets you excited and a little interesting. Thank you. I'll pass the applause along to the students. And yeah, that's right, the whirlpool. What happened in the whirlpool? About a year ago.
Supernova.
There was a supernova. Okay, well, I don't tell them about the supernova.
Oh.
I just go to the next, I just zoom in on it and say, well, let's compare an image from a little while ago to an image now. And this is actually from M101, but the idea is,
Same principle.
yeah, same principle. What's going on with this star? I mean, is it getting puffier, or is it getting brighter, or what's the story? Maybe it's just there's some differences in the images. Well, and you start to trick the students into going, well, let's find out. You want to find out? Sure, let's do that. And so how can we measure that? So what we do is, and this is a different field. I'm keep baiting and switching you guys. Sorry about that. You can compare 2 stars. And so we have some software that will help us measure how bright this star is and how bright this star is. And then I divide how bright this star is by how bright that star is. Okay, that way if we've got something that's filtering out half the light, this will be half as bright, that'll be half as bright, but the ratio will be the same. Okay? And so we did that with the supernova that I had blinking. A group of students from Maui High School actually worked with this with the supernova in M101, and they made this light curve. So here's the date, and each one of these, this is in Julian date, which basically is how many days since, I can't remember the reference date, but it's basically every one is another day. So 15 to 20, there's 5 days. And then this is the relative brightness. This is the ratio of how bright that dot that seemed like it was getting brighter was compared to another star. And we're looking at a blue filter. So we've got a blue piece of glass over the camera and the telescope so that only blue light is coming through. All right? And, oh, hey, it's getting brighter, and then it kind of rolls over, and if they'd had more data, they would have seen it trailing off. Okay? Well, that's kind of getting interesting, right? Have I lost anyone's interest and excitement from how cool the picture was?
Well, think of any planets that were going around that star and what happened to them.
Okay, that's great. Exactly. We'll let your imaginations run wild here.
What if our sun did that?
What if our sun did that? What happened to the planets there? What if E.T. was out there? Ouch.
Oh.
Okay. All right. So that's exactly what I want the students to do, is start picturing this in their minds. Start transferring from the visual picture to building an idea of concepts in their minds, a picture in their minds that actually becomes more exciting.
Also, you can see here that the possible lack of availability of a clear sky or the telescope, so you don't have a
Right.
continuous data stream.
Right, that's a good point. There's a big gap in data right here. And that was not all filters that gap was in, just the blue one. But yeah, you start seeing the reality of astronomy is we're at the mercy of these darn things called clouds. All right?
We're Hubble.
It's truth. Unless we're Hubble, and then we're at the mercy of other things.
Other people.
Yeah. We're at the mercy of government's funding and things like that. So let's think about what might be going on here. So this is the supernova. You know, pretty soon they catch on that this is a supernova, or the students look on a website and go, hey, we're looking at M51. There was a supernova there. Is that what we're looking at? You know, the students are very bright. So supernova, well, what can we say about that supernova? All right. I'm having issues here. All right, so what's going on? No, really, what's going on? Okay, so what's going on? We have a ball of gas. It's a star, and we know that it explodes. So it expands, right? Now, are we feeding energy into it as it explodes or not?
Not me.
Not me, not you. But is there energy being fed into this as it explodes? Okay, I'm getting a no. So let's go with that assumption. Okay? Learners of all ages, students of all ages, right? Okay, so let's pretend that we're not putting more energy into this explosion. We're not adding energy to the explosion by fusion in the core of the star or something like that. Okay? So as the gas expands, then it's going to cool, right? Okay? So it expands, it changes from blue hot down to yellow hot, then down to red hot. And then it keeps expanding and getting cooler and cooler. So each little section of area on this star becomes less bright in blue. And in fact, it becomes less bright in all colors. But it's also bigger, so there's more area. So it might be brighter, it might be fainter. So which is brighter? One bright light bulb or 50 faint light bulbs? Don't know. So let's start thinking about this. So I had the students actually model this, do some computations in a spreadsheet to figure this out. And I'll show you that in just a minute. But here's the actual observations. You can see the blue, where we are missing the data point from that night. I don't know why. The blue, the red, and the yellow. Okay? Actually, it's not yellow. It's green. I apologize. So red, green, and blue. And for the first few days, notice that the brightness of each one is about the same. So, and this is the ratio of how bright it is compared to the other star. So if these were all the same, then it would mean that would be an indication, but not proof positive. It's an indication that the temperature of that other star is the same as the supernova. Okay? And as it's expanding, the temperature is remaining the same. Well, that's really interesting. Kind of bizarre, in fact. And then you can see that, okay, blue kind of peaks out somewhere between here and here is where blue peaks out, and we don't know where. Or actually between here and here. Could peak out here and be coming back down by this point. But probably somewhere between those 2 points, looking at the trend. And unfortunately, we didn't have data to really constrain the peaks. And so the students, what they were really looking at is their prediction was that the peak brightness would be blue first, then green, then red. So the timing of when it reached peak brightness in blue would happen before it reached the peak brightness in green, which is a reasonable thing. And then, of course, when I was talking to the students about, this was submitted to the science fair, and they were saying, okay, well, how much of this project was given to us? And they're saying, oh, 75% at least. And I looked at them and I had to say, no, if you were trying to do what I was telling you to do, you misunderstood me. Very seriously, they did. They came up with this kind of on their own. I mean, it was misinterpretation of my guidance. I was very pleased with it. Okay, so if we compare to the modeling, temperature drops down, and I didn't have the graph that they made. The brightness drops down in all colors, all the time. The rate at which you're expanding does not compensate for how fast the temperature drops. Okay? So pretend that this is how bright it is in any color. Okay? So an adiabatic expansion would make the supernova cooler and fainter. Okay? So energy has to be added to the system. Somehow energy has to be put into the system in order for it to match our observations. But we can only see the surface. We don't know what's going on in the middle. Okay, maybe the heat is being transferred up to the surface from the middle, or something like that. All right. So I've still got you all enthralled. Good. I don't have to apply the emperor has new clothes principle and look at you and say, well, it's because you're not using your imagination. You followed this. Now, is this not an exciting project for the students? And these students went to the state science fair here in Hawaii. The Air Force in particular was impressed with this project. Okay, another project, and we have one of the students that's working on this project here tonight, stars with disks. And there are actually two subclasses. One is young stellar objects. The other is O and B stars. O and B stars are these very big, bright, hot stars. They live short lives and blow up spectacularly as supernova. Yes?
Short life, how long?
100 million years? Is that about right? Yeah. Okay. So, I mean, that's nothing. Our sun is somewhere around 5 billion years old, for comparison. And it's got another 5 billion years. Little tiny guys, the M stars, 100 billion years. Okay? So the young stellar objects are baby stars. And we know what's cuter than dogs and cats? Well, puppies and kittens, right? And so baby stars must be a really good thing to look at. Someone's going to have to take this controller away from me, I swear. All right? And those are really kind of the only two types of stars that tend to have disks. We're not sure why the O and B stars have disks. They shouldn't. They should be just blowing all the gas and dust away from them, but we see the gas and dust.
Would you describe what a disk is, please?
Well, that's a good idea. There we go.
A segue.
Beautiful. Yes, exactly. I didn't pay him to do that. Your check will be in the mail. Okay, you have a star here, and you have this ring of dust and gas around the star. Okay? And it's very, very, very large. And unfortunately, I seem to have misplaced my other image here. Let me see if it shows up. Nope. Okay? Very large disk of dust and gas around a central star. And I've chosen these colors purposefully because the star is hotter than the disk. Actually, the star, maybe, let's say it's a young star like our own sun. It's going to be kind of white hot. And the disk won't even be red hot. It'll be, sort of room temperature maybe. But room temperature glows in the infrared. Glows at certain wavelengths. And so we know how much light we should be getting from the star without the disk, and it's kind of a bluish spectrum. And then if we see extra red light in particular infrared light, then we can start to say, hey, there's a disk around this star. Okay? So identifying young stellar objects. Again, we got to show a pretty picture, otherwise, that's the real way to hook people. And all right, anyone in the room that has done research with me, do I really go through this plan of showing a pretty picture? And then, yeah, a couple of you, 3 of you are raising your hands. Okay. So, yeah, I show a pretty picture to get people excited. And then I start, well, what's going on here? What's going on here? I don't even always have to know the answers. So here's the pretty picture. We're looking at BRC 27. BRC stands for Bright Rimmed Cloud. So this is a cloud. It's a star-forming region. There is a very bright, an O or a B-type star that is making a shock wave through this cloud. And one of the theories is that that is what triggers star formation in this region. And so I'm working with a group from Caltech, Dr. Luisa Riebel and the Seaways team, which is a NITARP program. I'll get into that. Looking for young stars in this area of space. Okay? And the way we do that is the young stars will have a disk. They haven't had time to blow that disk away with their radiation, with the heat from the star, the radiated heat. And so we can measure, this line is what we would expect from a star. It's a kind of a black body. But down here, these are the actual observations. These pluses and other symbols are the actual measurements of how bright this point is. And so we've got this big excess of infrared energy. Well, what does that mean? It's a disk around the star. So we can see that. And so, yes?
When you said room temperature, do you mean literally room temperature? Like 70 degrees Fahrenheit?
Maybe not literally room temperature, but room temperature-ish. Depends on where you are on the disk. It's not like, hot like a star. It's not like cold in the coldest craters of Pluto. It's warm enough to glow. But room temperature, yes, we have a camera here at the IFA that you glow in the dark for this camera. You're warm enough that it sees the radiant energy that you emit. All right? So identifying young stellar objects. The project of this is to look, here's the cloud, and we want to see where the stars are forming. Are the stars forming along the rim of the cloud? Are they forming all through there? What can we learn? And so we're identifying we're identifying young star candidates in this by following this technique. This is a group of students. Most of that group are from the mainland. There's another group from Maui. There's at least 4 students in that group from Maui. Okay. Peer-reviewed paper in submission with teachers, like high school teachers, and students as co-authors. Now that's pretty impressive. Yes, let's give them a hand. Okay. And 2 of the points on here are like Falk's data. We're also using the WISE satellite, which is an infrared satellite, and various other data sources to combine. Spitzer as well. All right. So, asteroids, ninjas of the solar system. A couple of you remember my previous talks. All right. So, here's kind of the hook there. Can you find anything that's moving in here?
2 of them.
2 of them. Keep counting.
Oh, there's more over
I count 3.
4, 5.
1, 2, 3.
27.
I have 27. Do I hear 28? Did I miss one? This is, the things down here are kind of hiccups.
Is that one going off on the right edge of those, there's a pair of them?
Oh, those?
Tracking, or is that
No, those are probably cosmic ray hits or something. Okay? But you've got 3 asteroids. Notice they're all kind of moving in the same direction.
Yeah.
I think that that's probably that they're a family of asteroids. Anyone interested in looking into that?
You missed an asteroid.
I missed one? Where?
Wait, yeah, right up at the top.
At the top.
In the center.
This guy?
Down. There. Up. There.
Right there?
Yeah.
Flashing on and off.
Yeah, that's a hot pixel. Or that's something, might be a cosmic ray hit. Obviously, one of my these are my 2 of my asteroid students, and they're the ones that caught everything. Had a question, yeah.
How would you figure out the junk versus the real stuff?
The junk versus the real stuff. Do you see how the junk, it's very small, very sharp edges? But the asteroids are more like the stars in the field. The stars are all kind of fuzzy.
Is that because the cosmic rays only affect one pixel instead of a group?
Right. It can hit a group of pixels, but it just makes them all very bright. It dumps a lot of energy into each pixel. And so the stars are blurred by the atmosphere. And so we're actually zoomed in so much that the stars look like they're bigger than points. But they're really points.
How long is it between each of these exposures?
Probably about 15 minutes. I could find out if you really wanted to know. But typically the way I operate is that it's about 15 minutes.
Well, I see the diffraction pattern in these rotating a considerable amount. But
The
it takes
spikes?
A lot of time.
Yeah. Yeah, I'd have to check, but I typically go with 15 minutes. Maybe it was longer on this one.
So this was taken with the Fox telescope north?
These were taken with Fox, I believe, north, but I'm not
And the
absolutely
telescope
sure.
does this as well.
That's right. And so I have students will do follow-up observations for pan-stars.
Excellent.
Again, another excellent lead-in. Let's give my assistants a hand. Okay, so the idea, and we had a student from Maui High School, excellent gentleman. Oh, someone else from Maui High School. All right. Oh, no, this was from Baldwin High School, sorry. Yeah, so Baldwin High School had a student there that was kind of the first person that attempted this. Pan-STARRS was just getting going, and they gave me access to their database, and they had detections of near-Earth asteroid candidates. We couldn't get any predictions from the Minor Planet Center because they weren't handling them yet. So the student learned how to predict the positions of the asteroids. And the first thing you do is you use the equation of a straight line. So this is plotting the position of the asteroid versus time. This is, say, right ascension and time, then declination and time. And then you just you carry that line forward, and you can predict where it's going to be, and that can be good for up to a night. So if you can catch it the next night, you're good. Student also learned how to use a more advanced piece of software that was designed to predict the positions of these asteroids. And last I heard, he's over in engineering at engineering student UH Manoa. So another successful, that's the real success story. I don't care if they go into astronomy in particular, my students go into astronomy in particular. I care that they do something useful, that they enjoy, and sure, I'd like it to be engineering or science, mathematics, you know. Okay? So you measure the position, you predict the position, you take the observations, and the more observations you get, the better you understand the orbit. The easier, the more refined the orbit is. And then you repeat. So after you've observed 2 nights in a row, then you wait about a week and get some more observations. Then you wait about a month and get some more observations, and another month, and then we'll just catch it next year.
But your model's getting better all the way along.
Yeah, the orbit computations, you've constrained the orbit parameters, and so you know where it's going to be.
Even though this is on one night,
Mm-hmm.
I think it seems a little suspect to me that there's such good agreement with the straight line for all 4 points. Do you often see this?
This is very typical.
Wow.
Yeah. By the next night, you do see a bit of a curve. But remember that for the parallax, what's causing most of the motion in the sky is the motion of the Earth.
Yeah.
Yeah. Except for near-Earth asteroids, then they can be, they can be tricky.
Quixotic.
Yeah, a little quixotic. All right. So, another asteroid. This was one of my favorite projects. I was really geeked about this one. Student did very well. He went to the county science fair, and I was really pleased by that. This was the best of show at EL Middle School this last year.
Really?
I'm really pleased with the student, and it's really the student. Pardon?
Who was the student?
Picture him.
Back to you later.
Yeah, get back to me. I'm still recovering from being in Los Angeles. But yeah, I mean, great guy. And so Dylan. And so Dylan, I talked to him. He wanted to do a science fair project and kind of liked astronomy. So Dylan picked up this project that I wanted to do. Notice how that works. I want to do the project, so he's going to do it. Okay. And but I usually have a choice. I have several projects I'm interested in. Which one are you excited about? And this was a horseshoe asteroid, 2010 SO16. Some students that I was working with over on Kauai actually took some of the observations that constrained the orbit parameters, and to the point that we realized that this was this bizarre orbit for this asteroid. And what's happening is the Earth's orbiting the sun. And this asteroid slowly creeps up behind us, and then it gets pretty close, and then it slowly creeps away until it comes up in front of us, then slowly creeps away.
Weird.
Very bizarre. It's orbiting this Lagrange point, but it's an unstable orbit. It can only stay in there for maybe 100,000 years, something like that. So we have to ask, well, where did it come from? And where is it going to go? Well, we can figure out where it's going to go next. We can keep an eye on it. But here's a question. Everyone sees my watch, right?
Very nice.
Okay. Is this a gold watch?
No.
Okay. How do you know it's not a gold watch? Let me choose you. Because it doesn't look gold. Why doesn't it look gold? What's different about gold from this watch? Well, gold is yellow, isn't it? Yeah, is this yellow? So without ever touching my watch, you know it's not gold because of what? Because of the color. All right. And so here's the idea behind this project. Some researchers in Wales are the ones that contacted me about this target, and they wanted to measure the color of it. The reason to measure the color of it is so we can constrain where it might have come from. We know a little bit more about what it's made of, and so we can say, well, it probably did or did not come from the asteroid belt. And so that's what this student did for his project, is he observed this target, and poor Dylan, I mean, he had the worst luck I have ever seen of anyone on this telescope. We tried, I think there were 20 times that we tried before we actually got some good observations. And he submitted his science fair project on some kind of shaky observations, to be honest. But the reason he won is he had done good science. He's admitted, okay, it's a little shaky. He knew what he was talking about. He knew his asteroids. He knew what the orbit was. He could explain it. And that's the real point of the science fairs, is to get a good background and be able to explain your project. That's 80 to 90% of the point. And then doing the project is another 20%, which reflects real science. You'll spend 10 to 20% at most with the data, and the other 80% trying to figure everything out for the background. Yes?
The problem that you missed it 20 times, was it just not being able to predict where it was going to be at, or what was the reason?
The problem with why we missed it something like 20 times was weather, engineering, weather. Telescope operator screwed up once. Weather. I mean, it was just every time, it would rain one day of the week, and that would be the day, or, it was just something that hit that one time. I literally watched one time as the telescope slewed to the target, took like 2 or 3 images, and then closed. The weather went bad, so it closed. But he was really excited when he got the data and Dylan did an awesome job. Okay? All right, so what else can we do with asteroids? Some of you have probably seen this slide before. Pilfered from another scientist. But these are really great images. And so here's the test I always like to give people. If you've already passed this test, keep it to yourself. Let's let the new people try it. The idea is to take these 4 asteroids and match them to the light curves. So what we're seeing is this is like a photometer. It's measuring how bright that asteroid is versus time. And so this asteroid is kind of constant, dips down, comes back up, and is kind of constant, dips down, comes back up, it's kind of constant. This asteroid kind of bounces. So bright, getting fainter, getting brighter, bright, fainter, faint, brighter. Okay, and this one kind of goes around a little weird. This is small dips. So your challenge, and I've been meaning to put A, B, C, D on here for at least 2 years, so you can make fun of me for that. Match A, B, C, D with 1, 2, 3, 4. Does anyone want to take a guess? Yes?
Would number 3 be with B?
3 with B. No, that's close, though. That's the right idea. Have you done this before? Okay, go ahead.
1 with B and 2 is B. Wait.
One.
That's the corner one.
1 with D. Okay, just choose one. So 1D, that is correct. Okay. All right.
4 is C.
4 is C. You read your hand. 4 is C. Okay. Getting it? Okay. So we got 1D, 4C. Okay. What about these two? You know already. Who else? There's someone over here that had their hand up that hasn't already done this. All right? Who wants, we only have to match these two. Which one's going to be 1?
3
3 is
is A.
A?
Yeah.
Yep.
And 2 is B.
2 is B. There we go.
Like concentration.
Yeah. Do you see where the difference is? And you were very close. I see where you were coming from on your match there. All right? So the point of this slide is to let you see that we can, if we start watching how bright an asteroid is, then we, in principle, could measure how fast it rotates. Is that kind of in? All right. So not only do we have moving dots on a screen, we've got rotating objects. All right. So here's a project. These two students over in Hilo are doing this. Two students at Kamehameha Schools over there. Asteroid 1950 DA. Diameter 1.2 kilometers. This is, we don't want to get hit by it. All right? 1 in 300 chance that it will hit us on March 16th, 2880. Okay, I'm not going to be around. I'm going to be on Mars that day. But, you know, I've already planned the vacations that year. But, you know, we ought to be looking at this. This is, if this hits the Earth, it is very serious. You know, this is a planet killer. Okay. So this far out, so 800 plus years out, the difference between this asteroid hitting the Earth and not hitting the Earth is how much sunlight it gets. That's how small an effect it takes to change this asteroid. So what these students are doing is they're measuring the rotation rate very precisely. And then they'll compare it to what the rotation rate was 8 years ago. That gives us a measurement of how fast that rotation rate is changing. Okay, that's called the Yorp effect. And then by knowing what the Yorp effect is, we can predict changes to the orbit from the sun, called the Yarkovsky effect. In other words, these are superhero students who are trying to save the world. Sorry, the world of tomorrow. All right? And if, well, so, oh, that was not the one I wanted. But the Yarkovsky effect, there's a very nice, and let me get the right link here. Let me show the, oh, I'm sorry. Let me show the right link here. (1950 DA). So there's a nice link here. It talks about, without knowing who's doing this, it actually talks about the project these students are doing. Okay, they don't know who's doing it. You guys do.
Well, we have to fix it in Wikipedia.
Yeah, we should. We should.
Or they should.
I don't know. I'll have to see who wrote this. If it's somebody we know.
I don't want to contradict them.
Yeah, well, no. If it's somebody we know, we could just very easily say, "Oh, hey, by the way, let's put these kids on this." So now, is that just not mind-blowing?
Yeah,
That is so cool.
glad somebody's on it.
Yep. Okay. So there's that. Another project, and we've talked about this project a little bit here at one of the public talks, double stars. Okay, about 2/3 of the stars in the sky are binary stars. And by measuring the orbits of the binary stars, we can understand the properties of the stars. This is how we know that O stars are very massive and M stars are very small. This is how we know the relationship between the color of the star, the type of the star, and its mass. Okay? And so one of the things that we have some students working on is confirming that double stars are binary stars. Double stars are two stars that are near each other in the sky, but are they really orbiting each other? Okay? So we have two observations. Are those stars orbiting each other, or are they just passing by each other? You can't tell. You need at least 3 observations. And so we've got a list of nifty stars that have 2 observations, and we've got students to do that, and we got a powerful telescope that can do that. So these students can confirm that these stars are binary stars. All right? That is in the wrong place. Space, the final frontier. Look. These are the... Let me try. One more time. Space, the final frontier. These are the observations of the Falks telescopes. Their continuing mission to explore strange new worlds, to seek out new life and new civilizations, to boldly teach as no one has taught before. Okay. So even if you haven't seen me in my talks, even if you don't know me well enough, you already know that we're coming up on exoplanets, planets that orbit other stars. When I start talking to students about what are you interested in astronomy, one of the top things that pops up is exoplanets, which is a good thing because here's your typical exoplanet image. It's dots. And you get about 300 of these. All right? But this is where your imagination really kicks in. You know, we're seeing a planet orbiting another star. And so for anyone who saw, did everyone see the transit of Venus?
Oh, yeah.
Okay. You at least heard about it. Okay, so the transit of Venus, that was just really incredible. Here's the little dark spot on the sun. Okay? Exoplanets tell us about our own solar system. Are we unique? Are we freakish? Or are we common? Do star systems change? Do these planets suddenly decide to go closer into a star or farther out? And if we want to find life, well, everyone's seen Star Trek or Star Wars or Firefly or something, and so you know that the best place to find other life forms are on other planets. The reason we do transiting is, transits are about 25%. The reason we do transiting is this is easily done by the Falks telescope. And, well, it's easy to understand. I'm involved with it. That's why why transits are the most important thing, is I'm involved with it. Students here are involved with it. Am I missing any of my exoplanet transiting exoplanet students? I don't think I've got one here today. Okay. Yeah, he's not here. But we have a student here on Maui who actually helped discover a new transiting exoplanet, new exoplanet. And so we took the first time I got an exoplanet transit for a student. I couldn't wait. I just had to make a plot of the data. And Mr. DeVay from Baldwin High School shows up in my office that day. About an hour after I'd finished this plot, I was so geeked about it, I had to share it. And so we made this really great lesson plan on exoplanets. We had a student that was working with that data. And at 14, he went to the International Science and Engineering Fair. The American Association of Physics Teachers gave him third prize. And here he is competing against the typical competitor who was were juniors and seniors in high school. And here comes this punk 14-year-old from Hawaii.
With a lei.
With a lei. Yeah.
Fly your colors.
Exactly. So, and of course, now he's admitted to Stanford, Princeton, Caltech, and MIT. Though I think we lost him from exoplanets, he wants to do string theory. All right. But after that, of course, we made Travis teach the next generation. And this is where I really want things to go, is as students start to really understand what they're doing, I want the current crop of students to start teaching the next crop. Cheez-Its, yes. Colin loved Cheez-Its. We don't understand it, we just accept it about him. Okay. So, and here's a typical observation. Here's the simulation. Here's the observation. Okay? And what Travis was doing with his exoplanet stuff, and I'm not sure why that's not animated, is he was looking for a moon orbiting another star, or orbiting another planet, which is orbiting another star. What would happen is the moon would pull the planet around a little bit, and the planet would transit early this time and late the next time. And by measuring the timing very precisely of when those transits occurred, we could possibly find a moon. It would be the first exomoon detected. I still don't think they've detected one. Though 10 years ago they were saying, well, within the next 10 years we'll certainly have one. We haven't found one yet. So maybe Earth's kind of freakish, or maybe we're not doing it right. Yeah?
How do you measure the distance of the exoplanet from that sun?
From the star?
Yeah.
So how do we measure the distance of the exoplanet from the star? Typically what we do is we look at the color of the star. That tells us the mass. We know how long it takes for the exoplanet to transit the star, in other words, to orbit once. And so by knowing the mass and the period of the orbit, we can figure out the orbital radius, or the semi-major axis, actually. All right? So, what does it take to find an exoplanet? Was everyone wondering this morning? All right. Start off with the COROT telescope. COROT stands for Convection, Rotation, and Planetary Transits. It was put up by the French, the French equivalent of NASA and the European Space Organization and others. Does very high precision photometry, and has a large field of view, but not very high spatial resolution. So let me show you what that means. And so here's a picture of the satellite. Isn't it pretty?
Yeah.
All right. So here's an example of what we're talking about with the low spatial resolutions. This is actually a picture from the Phelps telescope. And it's not actually of one of their targets, because we want to keep their targets confidential. They don't want to be scooped. And so I had to agree, yes, I will keep these strictly confidential. Only the students get to see the data. Only the students will get to see the coordinates and the timing. All right, so this is just a random star field used for an example. So this is what their resolution is. That's the smallest spot that they can see, something like that size. Notice there are several stars in that spot. So this is basically what they see. Okay? Now, tell me, which star over here did you see that transit on? Okay? That's why they need ground-based follow-up. And the Phelps telescope is in a good position to do that. So I don't know. Which star was it in there? I don't even know how many stars there are in there anymore. So, your task, should you choose to accept it, right? I've got to follow with my themes here. Is to figure out which star has the transiting exoplanet. Okay, is there a transiting exoplanet there? Possibly. Maybe that dip is. See, remember that one? No? Yep. And we knew we only caught the second half of the transit.
So in other words, it went down like this.
So it's actually getting brighter here. So it was in the dip. The sun set about this time, or about here, gets dark enough, the telescope opens, and we start taking data, and then it's coming out of transit. This was,
Oh, I see, 'cause that,
yeah, this was a graph made by students. I did not make this graph. And it was a student from the High Star program. Okay? So how many of you are interested in one or more of these projects and want to become involved? You just need to keep bugging me. I've got some data for you. All right. Any teachers in here? Okay. Good. There's a really good way for you two to get involved if you're interested. Okay. Any students in here? Okay, you guys are already involved. Any students that want to become involved? Okay, that's more like, there we go. Oh, and you too. Okay, great, we'll get you. All right, so one way you can become involved is if you want to be part of the Maui Double Star Association. And these are, pardon? Yeah, these are some of the people in the Maui Double Star Association. This is me. This is Russ Janae. He's a researcher out in California. Steve McGee. I saw Steve come in, I thought. Rob Rakowski, who apparently is not here tonight. Everyone turn around and embarrass Michaela. Okay. So, we've got a few students here. This is not all the students that are in the group. And of course, the Falks telescopes are part of the group. These members observe double stars both visually using the eye and with the Falks telescopes. Members are expected to publish peer-reviewed articles. Okay. You think you can do that, Michaela? Yeah. Okay. You get a few peer-reviewed articles published while you're in high school. It's not a matter of getting into college. It's a matter of choosing which one you want to go to. It's a matter of who's going to give you the best scholarship. I mean, it almost is that to that point. As long as you've got decent grades, you've done some things, if you've got some peer-reviewed articles, it will get you very far. Even though this isn't the greatest journal in the world, maybe it's not even the most exciting thing in the world, but it's good science.
You're wearing the same shirt.
Yeah. I like this shirt, okay? That's right. It's like a callback, I've been doing callbacks to previous things. So, all right. The Maui Space Potato Hunters. This is a group that Kaylin was part of starting. It kind of didn't really take off because we were having a lot of trouble, and Kaylin was the only one that really plowed through and did some work with this. He's the student in engineering over at Manoa. But you could put together the Maui Space Potato Hunters again, and we could get that going. Yes?
What is that?
That's asteroids. Asteroids always look like a potato. I don't know why, they just do. So Maui Space Potato Hunters. NITARP. So teachers, pay attention on this one. NITARP stands for NASA IPAC Teacher Archive Research Program. Yes, the data is out there. The truth is out there. These are small groups of teachers and students. They work on real projects, like the star formation in BRC 27 that I was talking about, looking for young stellar objects. There's also another group that's working on exoplanets. The two teachers here are looking at the infrared background radiation. Two teachers on Maui. Having teachers apply to this and say, JD sent me, makes me look good. So if you want a pamphlet, there are some out on the front. You start off by going to the AAS meeting, the American American Astronomical Association meeting. It's in January. You go and you kind of look around and you get a little overwhelmed, but you go and see all these talks and these posters and, there's so much going on in astronomy. Then you start reading journal articles for the next 6 months, and you have kind of a journal review club, and you meet by phone. And then in July, you go out to Caltech, get to tour JPL. I just got back from this last week. It's an amazing program. And then you work on your project. You present it at the next January AAS meeting. It's a really great thing to do. Applications are due in September. Okay? The website is right down here. If you just Google NITARP for the virtual audience, you can find it. For those of you who are here who are interested, just grab a flyer. I'll show you where they are. The number one thing that the new people should know about this experience is that this experience is one of the best they will ever have. That is the feedback. That was a comment on feedback from this year.
And the Bazinga T-shirt.
A Bazinga T-shirt, yes. I was kind of disappointed. We should have both had our Bazinga T-shirts on. Yeah. So, what?
You kind of cherubic. You look a little cherubic there.
Yeah. All right. And this is Dr. Luisa Riebel who did that. Yeah, she's incredible. And this is the NITARP team I'm working with, the Young Stellar Object Group, the Seaways. All right. For students, how would you like a program kind of like that, just aimed for you? Come on, give us a good cheer. All right. Notice Mr. DeVay and Ashley and Michaela all have a shirt on with the same logo on the front. That's because they went to the High Star program, and they all walked away with a T-shirt. It's about a week-long astronomy camp. Another typo, good. And after the week-long camp, you spend the next several months preparing a science fair project. And this is where a lot of very good science fair projects have been coming from lately, including Travis. This is where Travis got his start. I don't know how many students we've had go to state. It's kind of to the point that, oh, I'm happy you're going to state. I'm not going to bother writing it down because it's almost routine now. I hate to be like that because it's actually a real honor to go, and not everyone gets to go. The application for that is due sometime in around February. So in January, you would start looking for that. Maybe call me up and say, hey, JD, what's the story with that camp? I can't remember what it was, but okay. So here's some student accomplishments. Last year, about 14 circulars. I know I put out 14 circulars, and I generally have students on them. I know there were 9 students as co-authors. Okay, I was a co-author too. Compare that to 120 at the IFA, at the Institute for Astronomy in total. That's pretty productive. 4 projects have gone to ISAF in the last 4 years, the Intel International Science and Engineering Fair. Travis got 3rd place from the American Association of Physics Teachers. I've lost count of how many have gone to state. Though congratulations if you're one of the ones that has. Peer-reviewed papers, 1 published, 1 in submission, 1 in preparation. And so thank you. Wow, I ran over. Sorry about that.
That's okay.
Any questions? Yes.
This might be too long, but if it can be done quickly, what's convection rotation?
Convection, it's 2 different things. The question is, what is convection rotation? And you're referring to the Corel satellite. So it's convection, comma, rotation, comma, and. All right. Other questions? Yeah.
With the horseshoe asteroid, have they found any other letters of the alphabet in the universe?
Have they found, with the horseshoe asteroid, have they found any other letters of the alphabet?
It looks like a C.
Oh, it looks like a C. Yeah, they found O.
If you rotate it, it should look like a U.
Yeah, we found C, we found U, we found N, and we found O. Other questions? All right. Well, let's go ahead and call it a day then.
That was a
Thank you.
very warm thought.
Thank you.
Very clear.